So as I've been introduced, my name is Scott Condron. I'm a machine learning engineer at Weights and Biases. So I'd love you to leave a comment just saying where you're from and introducing yourself, and maybe what you're hoping to learn from my talk about reproducibility. I'd also love to hear like maybe where people are on their reproducible machine learning journey. Like, are your experiments reproducible at the moment, or is that something that you're sort of waiting and need the motivation to get to the next step of reproducibility? So with that, I'll just dive into the agenda. So what I'm just going to briefly talk about is an introduction to myself and give a bit of background around why reproducibility matters to me, and maybe my perspective on things. Then I will briefly talk about the barriers to reproducibility, why I understand like it is actually not the easiest thing to achieve. And then I'll talk about some of the benefits, hopefully motivating you to take those next steps of making your machine learning work more reproducible. I'll give you some advice for quick wins to do that, and then I'll talk about weights and biases briefly at the end. So this is me. So I was a software developer, but now I'm a machine learning engineer. So I didn't come into machine learning from academia. I came more from the software world, where I was sold the dream of DevOps and continuous integration, continuous deployment, that kind of thing. Where you're building processes around your work. So you're kind of protecting yourself from yourself. We acknowledging that everyone makes mistakes and that bugs are quite quietly introduced. So you've got systems in place that will catch those. So when I transitioned to machine learning, I quickly realized that I kind of wanted a new set of tools that would help me in this new paradigm. I was thinking, okay, there's a lot of additional complexity, a lot of different moving pieces, and reproducibility was really on my mind. So I was like, how do I make sure that when I run my code or when I try a new experiment, that just because I've written that result down, I can actually go back and achieve that or find and get that result from my models. Questions like, how do I track and plot results? How do I visualize my data? How do I track my models? Those were front of mind, and it was I was kind of reaching for tools to help me with that. And at the same time of thinking about reproducibility in the context of my own work, there was a broader conversation around reproducibility in academia, where this is just a random article I found on The Guardian that was talking about a study where these researchers tried to just take, say, 21 experiments from big journals like Science or Nature, and they found that they could only reproduce 13 of the original findings. This is obviously a little bit different to the machine learning and the work that we do, but I think that broader conversation still probably rings true for a lot of people, especially in academia, where machine learning, there's a lot of complexity, hidden technical debt, or a lot of pieces needed for reproducibility. And yeah, I can imagine if they ran this experiment for machine learning projects, it wouldn't be much different. So the additional complexity, sometimes this is kind of what it feels like to manage all of that. So I can relate to this guy trying to bundle all his tools together and make his way to clean his car. But once you acknowledge that reproducibility is a problem, there's a lot of bad solutions that people come with to try solve them. And I think it requires a little bit of upfront work to put in that effort to make your work reproducible. But yeah, like I think we can all relate maybe to this guy's pain. So the main point is with the bad solutions is that there's I think you've at least acknowledged it's a problem and you're trying to solve it. So there's no shame in some of these bad solutions that people come up with. For instance, you realize that you want to track your hyperparameters that have gone into a given model. So that something that people reach for is like dumping all of the hyperparameters into the file name. I've been down this path before. I actually did a quick bit of back the envelope math, and my current estimate is you can jam 32 hyperparameters into a file name, which that's limiting to 1 letter per hyperparameter. So if you guys want to go off and before you hit the file length limit, by the way, that's the limit. Some systems won't let you name a file any bigger than that. So, you know, there's no shame. We've all been down that path, but at least you're acknowledging it's a problem that you're trying to solve. As opposed to that little emoji on the left where it's just like, it worked on my machine at that one time with that data. And here's the result. So just take my word for it. It's a good result. So obviously that's not the approach I hope you come away from this talk with. And then there's also the other bad solution, which is to put it on someone else. So just you have a .pth file or a model file, and you just say, here, go reproduce that and go make that, you know, go make that a good model or good robust system. I think how I saw the world when I had come into software, it was that the story I was told was before test-driven development was a thing, engineers would just hand off their work to test developers, and they would write tests for their work. So I think the same is we kind of live in that world now, whereas there's a bit of a difference between some research or ML code is allowed to be messy, and then it's like handed off to someone else to be cleaned up and made reproducible, where I think that will converge at some point, and there will be a bit more of an onus on the person actually doing the research to put in that effort to make their code more reproducible. But yeah, there's a lot of factors that change with regards to machine learning. Your code can change between experiments, your data, your environment. So I'm not here saying it's easy, but I'm saying it's worth the effort. So that's where we are now. I think you often hear the sentiment, isn't reproducibility too hard? Like, why do I need to have my code run? It ran once, please leave me alone. But hopefully after I give you some of the quick wins, you'll be a little bit more motivated to make that next move. But I acknowledge there are barriers to reproducibility that are worth acknowledging. So this image on the right is from a great talk that I highly recommend people check out from Kirsty Whitaker, where she talks about some of the barriers to reproducibility. And the big one, and the one that I think we could probably all relate to, is that there's limited incentives to give evidence against yourself. So people would plead the fifth and they'd say, no, I'd rather not incriminate myself and share my work, because otherwise people will find my mistakes. But I think we need to build a culture where mistakes that are found are better than mistakes that are quietly hidden in someone's repo or whatever, and that we allow people to make those mistakes, and we acknowledge it's human, just like the DevOps world, where they acknowledge that everyone makes mistakes, so they build systems to catch those. I think machine learning, it's the same. We're kind of in that same world, but what mistakes means is a bit more complicated. There's also additional upfront effort needed, and that kind of goes without saying. And you've got to learn the few tools you need, say, to make your work more reproducible. And then you've got to do work at the very beginning of your project. So it's like you're given the data set, you're given the challenge, and you really just want to dive in and start experimenting with the latest cool model that you found. But you should be encouraged to do that initial bit of work preparing your project, so that as you start experimenting, those experiments are captured and your work is reproducible. Now, this is a bit more nuanced, and maybe the final 2 points are a bit more nuanced, and it's a bit more relevant to academia. But with regards to, say, academic reproducibility of papers or reproducibility of academic papers, you do need, in a lot of cases, massive compute to reproduce them. And you, if they haven't shared the code, or if they haven't shared the data, what chance do you have of reproducing a given experiment that's written by some big research lab or big company? I'm not going to really touch on that, but I think the nuance there is that reproducible experiments doesn't necessarily mean open experiments. So their work could still be reproducible, but just within their organization. And just because it's not open doesn't mean it's not reproducible. But that being said, I think I would love to see a world where these papers were shared more broadly and the data sets were shared more broadly, but that's not the point of this talk. The benefits of reproducibility are many, and I hope greater than the cost of, or the barriers to reproducibility. The first one, and I think this kind of encapsulates everything, is that it improves efficiency for long-running projects. So you, by doing that upfront work, learning those few tools you need, then you know that, let's say you have run a bunch of experiments, you go off, you run a bunch of more experiments at a different project, but then it's crunch time and you're starting to like write your paper, or you're really pushing to get your work into production, but you want to go, okay, where's my best model? Like, I need to find that one best model. Because you've built this system, it'll be a much more efficient to just boot up the environment, find the best experiment, and be comfortable with and confident that you found the right model and you can just deploy it or write about it in the context of a paper. Where if you hadn't done that work, you'd be spending all your time, or all that time, just trying to get back to where you were, so I think that that kind of goes without saying anyway. You've made it more reproducible for yourself, and then when you want to pass it off to someone else, you make it easy for others to collaborate and get started. So they're coming along and they're saying, like, imagine someone coming along and going, here's a bunch of my spreadsheets, here's a bunch of random .pth files, make sense of this and build on it. That's a bit of a straw man maybe, but there's that's a much worse world than if you had made it neat and reproducible for yourself. You could pass it off and then they can start reviewing and contributing. And what that'll do is, by them reviewing it, it'll improve the validity of your own work. So that someone else has tried it, so you're able to sleep at night, that you're not lying to the world. And then you also know that if you go off and work on something else, potentially that person will continue your work, build on top of it, and that it's not just wasted. It's not just only you that has done that thing. It's now being continued without you, because you put in that work to make it easy to get started. The final point is a bit more in the context of maybe an organization, and that's just to say that, like, if you don't incentivize people to do that upfront work to make their work reproducible, and you don't really encourage that culture inside your organization, when some machine learning engineer goes off, as they find a different opportunity somewhere else, or for whatever reason stop working in your organization, or even just move to a different section of your business, they'll have taken a lot of the intellectual property that you value and that is providing value to your organization. So they'll, what use is a bunch of models on their local machine and a bunch of institutional knowledge that they maintain. That's like, why did they run their experiments? What was the results they found? You don't want to be asking them, hey, can you send me all your spreadsheets or on all your presentations so we can make sense of your work? So I hope if you come away from this talk with anything, it's that reproducibility isn't a binary 1-0 where it's either not reproducible or reproducible. I hope you come away with it thinking that reproducibility is a scale where things are less reproducible or more reproducible, and more reproducible is better. So there's a bunch of steps you can do to go down the path to be where eventually you think your work is like entirely tip top and reproducible. But there's a bunch of steps. So if the quick wins I would recommend is, let's be clear. The first one, I mean, maybe I have a biased perspective here as a software developer who works for a machine learning tools company, but my pitch is to embrace tooling. That's a bit of a hang up of the world I came from, which was in software development, where they really tools and building systems for themselves to protect themselves from themselves is kind of the main goal. So if you're not using source control, I mean, that's ground zero. But other things that maybe smaller businesses would have less adoption for, that I encourage people to get started with, is something like experiment or environment management tools like Docker, or even something as simple as Conda, which is a little bit less powerful than Docker, but you can still use it to capture the state of your environment and maybe some of the dependencies that the code relies on. And then finally, rethinking the inputs and outputs of your code as like a first-class citizen. So in the context of software development, logs and things like that don't have as much value as they do in machine learning, where you really care to like see the metrics that you're logging as you're training. They have a lot more value in the context of machine learning, and the inputs to your code also can change quietly without if you're not tracking them. So you want to track every run of your code and all of the things that code depends on, or outputs. So your logs, or your models, or your input data, and your hyperparameters. Those are now first-class citizens, and you should treat them as such, as opposed to treating them as an afterthought. So that's the pitch anyway, is to track each run of your code. And the tool of the organization I work for is Weights and Biases, and I'll briefly talk about sort of how we approach the different aspects of making each run of your code more reproducible, as opposed to, say, what source control is, where it's just tracking the static version of your code as it is. So the main point of this slide is to say how every organization, every section of a business will have their own set of tools to keep track of their work. And Weights and Biases is pitching that we believe that our tools should be the central place where you store all of your work as a machine learning practitioner. So it's your way of just keeping track and having a system of record for everyone on your team to keep track of your ML work. And what does that look like in practice? It's a bunch of different tools specifically built to target different problems that machine learning engineers have. Our bread and butter is experiment tracking. So that's where you run your code, you get logs, you've tracked the input hyperparameters, the input data. And you can see you and your team's models update in real time and monitor all your experiments. It also allows you to automatically organize your training runs, logs, and models. So that's what dataset or 1DB or Weights and Biases artifacts is a dataset versioning and model checkpointing solution, where every new version of your dataset or every new version of your models are tracked. And I'll talk briefly a bit more about both experiments, artifacts, and reports later. And then there's Weights and Biases tables, which is a bit of a new feature, which is a neat way to visualize and interact with your model predictions. And then we have a model optimization or hyperparameter tuning solution called Sweeps. And finally, one of my favorite features is weights and biases reports, which is a neat way to collaborate and share your work and your plots alongside text with other people on your team. What's nice about weights and biases is it works on top of any framework you're using. So we're kind of agnostic to the other tools you're using. And we also are agnostic to what environment you want to host weights and biases on. So we have a hosted solution that we provide, but also you can run it on premise or in any cloud service that you're using. So in practice, how you would integrate weights and biases into your code to start making your work more reproducible is just pip installing a Python library, creating a little project with a name. So you can think of that like for a given model, you would have a project name, and then entity is just a team name. So whether it's just an individual or whether it's a team, in this case, the team name is the Jeffrey Hinton Fan Club. Then you pass in your hyperparameters to a weights and biases config, which will store them every time you run your code. And as you're running your code, you log the metrics, and they will be visualized in interactive plots on our web-based UI. So I'll quickly dive into the different components. So as you're running, this is kind of what the UI will look like. It'll just plot some of your, so these are two different runs of the code, or no, these are two different metrics being shown for a given run. And we also have another way to aggregate that and show all of your runs side by side. We'll track all the different things that change between experiments. So to ensure reproducibility, you want to only change one thing between every experiment. So that you can, you want to track everything that changes between the experiment, but to make sure you're doing rigorous science, you only want to change one thing. So you can change your data, you can change your training pipeline, you can change your hyperparameters, your development environment, or the code. And weights and biases has a solution to capture all of that, which looks like this, where it'll also pick up a bunch of other things that you don't have to log manually, like what system you were running on, what command you ran, and maybe the Git state or any uncommitted changes in Git, which often machine learning engineers do. They'll change a hyperparameter in a random file and run the code. So weights and biases will automatically capture that and create a patch that you can use to make to go back and check out what the state was. And it captures a bunch of other useful things like what the GPU utilization was and what hardware you're running on. And then the configs and the logs that you've plotted are persistent and stored, which will allow you to query and filter across all of your runs and keep your projects organized. So you can add tags, you can add notes, you can group by and filter depending on what analysis you're doing. Finally, then once you kind of have your analysis, let's say you want to store this plot, or you make a bit of a fancier plot that compares a bunch of runs and shows like, oh, as I train longer or I use this certain learning rate, the training accuracy is improving. Or you want to filter and you say like, every time I ran with this architecture, this is the plot that I've gotten. Because you've already logged those, you can generate those plots after the fact. So you don't have to know what experiments you necessarily will want to share with the world. You can run all of your experiments and follow the wind a bit, and then you can go after the fact. You can really go in and fine grain and analyze how your runs did, snapshot that, and then you can share them in what we call weights and biases reports. So you can think of reports as like a text editor with your interactive plots, where you can just dump down all your brain dumps. So you go, oh, I just want to, I have a streak of inspiration right now. I want to write down all my my thoughts, or you've got some eureka moment that you want to store for future, or even if you just want to say where sorry about that. You go, I want to see where my experiments were at a given point in time. That's what weights and biases reports are for. And they play nicely with everything else in weights and biases. So once you have all that analysis, you know that you've tracked your runs, you've tracked your hyperparameters, you've got all your plots and your analysis, and you've shared them in reports. So this kind of comes back to that anecdote of imagine if someone arrived to you and was like, here's a bunch of unexplained charts and spreadsheets, go make sense of them, go make this reproducible. Weights and biases reports exist, so you don't have to inflict that pain on yourself or anyone else again. You can share your analysis alongside the actual runs that produced that analysis, so that people know this is an evergreen interactive snapshot of my work that's not going to go stale and not going to become inaccurate or not reproducible. Finally, I'll briefly touch on weights and biases artifacts, which is basically our solution to tracking your models and your data. So what you do is you just integrate your code with weights and biases artifacts, and you save your models as artifacts as well. And then every time you run your code, weights and biases will store the inputs and outputs of your code, and they'll build this rich lineage graph of, for a given run, who ran which model, when, on what machine, using what code, on what data. And you can visualize that in a big exploding graph like is in this screenshot here. So that'll help you get model IP out of one-off slide decks or off people's machines and tie it directly to the data that actually trained your models. So that is it. I'll leave, I'll be in the chat if anyone has any questions, but I've finished a few minutes early, which is never a bad thing. So I'll be in the chat to answer questions for a while. And if you do want to reach out, you can check out weightsandbiases.com, reach out on Twitter. I'm always in the forum as well. So if you want to ask me any questions, you can reach out on the community forum, which I'll be answering questions. Thank you very much for your time.